So good afternoon, everybody, and thank you for the introduction. I believe I'm standing between you and coffee, so I would try and make this as interesting and engaging as possible, and then we can have that break. My talk is split into two sections. The first one is an introduction to Oneweb and something about our network, and the second section is the role of LEO satellites beyond 5G, in other words, 6G. So some key facts about Oneweb. We're based in London. I think I'm still on London time. It feels like 6:15 in the morning. We now have had 14 rocket launches, not 13. The last one was from India about 10 days ago, something like that. There's more to come. With each rocket launch, there are 34 to 36 communication satellites which are launched at any one time. So far, we've deployed more than, I think it's now 450 satellites, something like that. So this slide is already a bit out of date, with 7 launches in the past 12 months. We also have a ground network which complements it. So that's ground stations spread around the world and backhaul connectivity from the ground stations back to points of presence to allow connection back into the internet. The two pictures below are of our satellite manufacturing facility in Florida, in the US. These produce about 2 satellites a day. It's largely robot controlled and sort of just in time and things like that. The diagram here shows, the block diagram shows something about the satellite itself. You can see the purple antennas are for the feeder link, which is in the Ka band. And then you can see, if the pointer works, this is the user link antenna array, which creates a bit like a Venetian blind, which sweeps around the Earth as the satellite's orbit. You can see the solar panels on each side. Each antenna is about the size of a fridge. So, each satellite is about this wide and this high, something like that. They're in an orbit of an altitude of around 1,200 kilometers, and they are not quite, but nearly a polar orbit. The picture here shows the satellites stashed in the frigate, which sits on top of a rocket, and that's what gets launched up into space. This is a block diagram of the system itself. So let's start with the satellite in the middle, and we have a procession of satellites as they orbit round, serving the users and connecting to the gateway simultaneously. So on the user side, we would almost certainly connect to airplanes, ships, industrial and domestic buildings, cars, trains, and hey, why not in the future, UAVs and even other satellites? A plausible scenario. On the other side, the ground network side, there's our operation centers, gateway antennas, and then to the points of presence and out to the internet. In terms of spectrum rights, we have priority filings in the Ka band and the Ku band. Latencies of around 100 milliseconds, and then download speeds of up to 195 megabits per second. So that's just an overview of our system today. And eventually there will be some 648 satellites when the remaining launches will have gone up. In terms of use cases, I won't go through all of these. You can see the pictures quite clearly yourselves. But the one which I do quite like, and just to point out, is connecting rural schools and communities. So my children at school, they have internet, they're allowed to use it. When the teachers say so, it's part of teaching and learning these days. But imagine a school that doesn't have that, and being able to bring that to those teachers and pupils would revolutionize their teaching and learning experiences. What about the user terminal themselves? Well, we are imminently moving towards electronically steerable antenna array-based UTs, and you can see a picture of some of them on the screen. So these are based on antenna arrays, as the animation here shows. You can have an array of antenna elements phased appropriately, and that would steer and follow the satellites and give enough gain to serve the user's needs. So these will bring up new opportunities for aviation, trains, vehicles, man packs, but not without challenges. We have to make sure that we adhere to the ITU EPFD regulations, and also the G over T, the gain over temperature versus aperture size, is a challenge which one needs to be mindful of as well. So if this works, and don't press the button just now, give me 1 second to explain. This is a short video, about 3 minutes long, which was made about 1.5 years ago, so it's way out of date in a way. But the reason why I like to show this is because it shows not really the kind of marketeer's perspective, but the engineering perspective of one of the early experiments of connecting a UT in Florida back to the office in London. And so when this plays, hopefully, fingers crossed it will work, you would just see what was a live experiment 1.5 years ago. We now have way more satellites in space orbiting around, but this is a nice technical engineering example. So fingers crossed, if you would mind pressing play, that would be really helpful, please.
Oneweb is a global network of satellites that cover the whole Earth, connecting everyone, everywhere. We're here in Melbourne, Florida, to show an early pilot of our satellite network, and we're going to connect our user terminal to the satellite network and back down to Earth, so that our customers can see the speed and the low latency and the maturity of our network. This is our gateway antenna. So this antenna is talking to our spacecraft, our fleet of spacecraft as they move overhead, and then talking to literally hundreds of user terminals. So it's connecting the data from the internet, from the cloud, over our satellite network and to our end users and their user terminals. So this antenna is pushing hundreds of megabits per second of data out.
Here we are connecting to the Oneweb satellite on this orbit. So here we have the satellite number 95, which go over Florida, where we are connected.
Very confident about this one.
Yeah, it's going quite well. The SNR are good, and the data rate seems very good. So perfect. Yeah, the SNR is the ratio between the signal received and the noise at the terminal side. So this is a metric that we are using to assess the quality of the communication. So here we have around 15 dB SNR, which is very good. And we managed to get 500 megabit there.
Wow! That's great.
So yeah, we can ping there.
Ping session running here. So 32 is
39, 36.
Yeah, 37. Yeah, you can show.
Last time you made 27.
Here we go. I can kind of share the screen. You can ping it yourself in the thing. So I think what's really key here is that, like, I can see you guys speaking, and the sound is complete. The latency tells the story here, right? This is perfect.
Here you can see that there is two antenna which are tracking our satellite and switching from one satellite to another when there is handover.
Seeing here is every couple of minutes we hand over, every 11 seconds we're handing over beams, every few minutes we're handing over satellites. But there's no impact on the team session, right? There's no pixelation, there's no jitter. Perfect. And back down to purity of our
I want
net.
to go to the next slide. Got it, right. Okay, so I've given you an introduction now to OneWeb, to our network as it stands today. And now what I'd like to do is look to the future a little bit with 5G and beyond, and something about the drivers and timeline. But I want to start with a bold statement, really, and this is not the first time that this has come about, I've noticed in the last day or two, but a unification of terrestrial and non-terrestrial networks as a key theme which is coming out towards 6G. But in the true spirit of non-terrestrial networks and terrestrial networks working together, then we could look at an example, and there's the potential merger potential between Eutelsat and OneWeb. So that's bringing together GEO, LEO, and of course the necessity of terrestrial networking, which goes with it. So splitting these based on, splitting the quality of service profiles of the users based on latency could be one way of doing it. And I have just put some examples down here of various applications and how they could be split dynamically between the two services when required by the terrestrial network. So what about standardization? And it's probably fair to say that this is the first time that non-terrestrial networks have been indelibly baked into 3GPP standards. I won't go through the details, but in release 17, quite recently, that was the first breakthrough. We have the forthcoming release 18 with a little bit more, and release 19. So that is certainly showing a trend. So what about 6G? And what are the drivers behind 6G? Why should we care? Well, there are a number of use cases I've put down, but I'm just going to pick out the one in the middle, really, and say, well, hey, maybe the driver behind all this is the metaverse or other names and words given to that, and the needs of that in terms of connecting people anytime, anywhere, and better experiences online, 3G video, haptics, tactile internet. We've heard this several times already in the last day or two, but maybe that is actually what is driving the need for 6G. And when you can understand that, you can then think, what does a system need to do? So then the layer on top of that is, well, what does NTN and terrestrial networks need to do to make this work together fully? And so that really brings about this diagram, which shows, or tries to show, where uniquely satellite comms or non-terrestrial networks could fit within the world of 6G. And if we start in the outside ring and coverage, well, yes, satellites can provide global coverage, but that's not specific to 6G. That's 5G, 4G, and anything else. It can backhaul networks, and I'll show you a project in a minute which shows backhauling 5G. So that's not unique to 6G either. One day, satellite communications could deploy a 6G protocol stack. Yep, get that. It could provide positioning, navigation, and timing services to be able to support the necessary quality of service profiles in 6G. It could provide key distribution, encryption key distribution, specifically for underpinning the security requirements of 6G. So yes, those could be two unique elements of SATCOMs to 6G, notwithstanding the rest. So what does this mean for satellite communications? Well, again, I'm not going to read this list out. I've already mentioned some of them, but just to pull out a few extra points. Spectrum, spectrally efficient waveforms, interference management, and spectrum sharing. Regulation and standards that influence the interoperability. And then integration of a range of user devices, seamless integration. And specifically from a satellite perspective, then we need to think about constellations, orbits, and launches. Without launches, you're not going to get very much up there. Of course, responsible space and space debris is super important. And open standards to promote interworking of different supply chains. And we've heard a little bit about O-RAN and open networking in the last day or two. And then above all, a viable economic and business model, because if that's not in place, again, nothing's going to happen. So just to finish off, I want to touch on two research projects that I've been working on. And one is funded by the European Space Agency, and it's called 5G Pilot. And this is in collaboration with the University of Surrey. And what this is doing is it's using the OneWeb constellation to backhaul 5G G-Node Bs. So the scenario is quite simple in a way, in that at the University of Surrey, they have their own 5G network, and similarly they have a 5G core, and the idea is to connect the G-Node B back to the core using our satellite communication system. So that means making sure that the quality of service is there end-to-end, supporting a range of services which I've listed here. So we need to make sure that latency is managed, the uplink and downlink data rates are balanced, and then prioritization and buffering is in place to support it all. The second one I just want to touch on is, it's finished now, a research project with the Royal Melbourne Institute of Technology in Australia, and that was supported by the UK Space Agency and the Australian Space Agency in something called a space bridge. It's a virtual bridge, not a real bridge, between the UK and Australia. And this is about rain phase modeling around the world. And so rather than focusing on the Ka and Ku bands, this is at the Q band and V band, so 40 and 60 gigahertz. And being able to model rain fading at those frequencies, but also for the range of elevation angles that you can expect with orbiting satellites, which we are not used to and not needed with GEOs. And the way we went about that was we used data from AlphaSat. AlphaSat is a GEO satellite, so geosynchronous orbit, and data taken at a couple of points on Earth, and then weather data from relevant points on Earth as well. And then we used some machine learning techniques to put together a model such that we can model fairly reliably the rain fade as a satellite passes over. So this is there's just one example of a result here, where we have time along the bottom x-axis, and then elevation for one particular pass, peaking at about 65 degrees, and then you can see the results here of the excess path loss through rain fading, and it's higher at the edges because, of course, the signal has to go through more atmosphere to reach the satellites. So there we are. That's what I have to say. I've provided an introduction to the Oneweb network, something about the future, so 5G and 6G and SATCOMs, and then touched on a couple of research projects. Thank you very much.
Thank you.